Hello students, welcome back. In this video we are going through chapter 3, section 3, which is measures of relative standing and box plots. Now this, I'll give you a little bit of a warning, will be one of the longer videos that we've done up to date, but it is, I assure you, the most significant and important section that we have done thus far in this class. So it's important you understand the concepts that we discuss here. So the key concept here is that we are talking about relative standing, or how a number compares to other numbers. And let me give you a quick example. Say you take a test in one class, and the class average is an 80, and then you got an 85. And then in the other class, you scored a 90, but the class average was a 92. So clearly you personally scored better on test 2 with the 90, but if you were asked which test did you score better relative to the class, that's that relative standing term, then you would have done better on test 1, where you actually exceeded the class average. So again, we are using relative standings to be able to compare apples to apples when determining how you did compared to others. The most important concept is the z-score, which is the way that we measure relative standing. We will also discuss percentiles and quartiles, and graphical ways to depict percentiles and quartiles. So without further ado, a z-score is a standardized value. It's a way that we take any data value, once we know the mean and the standard deviation, and then we figure out how far it is away from the mean. It's how many standard deviations a given x value is above or below the mean. And it is calculated by using this formula right here. You have your z-score equals the x value you're interested in minus the mean divided by the standard deviation. And that will kind of normalize any value, and that will give you a number, a z-score, usually a number between 1 and 3. And that will tell you how many standard deviations you are away from the mean. So if your x value happened to be the mean, then it would be the mean minus the mean, which would be 0. Any 0 divided by any number would be 0. So clearly an x value that is equal to the mean would be 0 standard deviations away from the mean. So we're getting a little wordy, so let's just move on. So important properties of z-scores. A z-score is the number of standard deviations that a given x value is away from the mean, either above or below. Above would be positive z-score, below the mean would be a negative z-score. Z-scores are expressed as numbers with no units or measurements. If you look at here, the units would end up canceling, so you have a unitless measurement. A data value is significantly low if its z-score is less than or equal to -2, and significantly high if its z-score is greater than or equal to +2. And that's kind of similar to what we did in previous sections, where we said if it was in between -2 and +2 standard deviations, that was considered not significant or normal or expected, since 95% of data values will fall between these two ranges. So significant is going to be lower than this or higher than that. And then if an individual data value is less than the mean, its corresponding z-score is a negative number. Because you're taking this number, you're subtracting a larger number, you're going to get a negative value. If the x that you're looking at is larger than the mean, you're going to get a positive value. Larger number minus a smaller number is positive, and then standard deviation is always going to be positive. So let's look at the z-scores from the test example I gave you last section. So a student received an 80 on test 1 and a 73 on test 2. Which of the tests did student A perform better in relative to the data from which it came from? So we're not just saying, oh, 80 is greater than 73. He or she did better on test 1. No, we're saying which one did they perform better relative to the data set for which it came from. So we have to find out 2 z-scores, one for each test, and then compare those values to each other. Now it's our way of normalizing it so we can compare apples to apples. So let's go on. So for test 1, the formula is the z-score is equal to the x value of interest minus the mean divided by the standard deviation. So the x value for test 1 is she scored an 80. The mean is 70. And the standard deviation for test 1 was 21.46. Okay, so her z-score is 0.46. That means that 80 is 0.46 standard deviations away from the mean, which is 70. One more time. 80, the score that she got, is 0.46 standard deviations away from the mean, which is 70. So let's look at test 2, and we'll do the same thing. The mean is also 70, and she scored a 73 on that test. So 73 minus 70 is 3. Divided by the standard deviation of 2.16, and her z-score is 1.38. Okay, so even though let's look at our conclusion. Even though the student received a higher score on test 1 and received a score, was that poorly worded, and received a score higher from the class mean than the test 2, the student performed relatively better on test 2. All right, let me just word that without reading off the screen. So even though she scored better on test 1, clearly 80 is higher than 73, she actually scored better relative to the rest of the class on test 2. Why? Because 73 is 1.38 standard deviations away from the mean, whereas 80 is only 0.46 standard deviations away from the mean. Another way to look at it is, hey, let's just look at it intuitively. She scored an 80 on test 1. Well, that means that 2 other students scored better than her. On test 2, she scored a 73. Oh, look, 73 is the highest grade in the class. So look at how much further away this is than the mean compared to this is from the mean. Just a little way to look at what we're doing. Sorry about the wording of that. I have to go ahead and fix that. Okay, let's look at another example. Comparing a baby's weight and adult body temperature, 2 extremely unrelated events. But the point here is that you can take any unrelated, related event, and once you apply a z-score, you normalize it, meaning that now you can compare apples to apples. You can always compare these z-scores to each other, because before you can use the z-scores, these numbers really mean nothing to me when you look at them side by side. They're just too unrelated. But the z-score kind of bridges that gap to make you be able to compare them. So which of the following 2 data values is more extreme relative to the data from which it came from? So the 4,000 gram weight of a newborn baby among 400 weights, and the sample mean is 3,152 grams, and a sample standard deviation of 693.4. Okay, so we have our x value, we have our x bar, our mean, and we have our standard deviation. We can get our z-score. Let's go on to the second data set. The 99-degree Fahrenheit temperature of an adult with a sample mean of 106 adults having x bar is 98.2 and a sample standard deviation of 0.62. Again, we have our x value, our x bar, our mean, and our s, our standard deviation. So we can get the z-score of that. We'll get the 2 z-scores, then compare them. The more extreme z-score is going to be the more extreme value relative to the data set from which it came from. Okay, so now we'll get those 2 z-scores. So for the birth weight z-score, we take our 4,000 gram birth weight, we subtract our mean, which is our 3,152, and then we just divide by the standard deviation. Now this is a formula that I will expect you to be doing yourself with your calculator. And even though it's this very simple formula, a lot of students make a mistake on it. So I just want to quickly show you how I do on my calculator as well. So let's kind of look at a calculator. Okay. So when I do this, now follow up, alpha y equals enter. And that will give me numerator over denominator. It'll just give me a nice little fraction. Because now I'm a very visual learner, so I like to see what I'm typing in. And there's your z-score. Of course, you can always do 4,000 minus 3,152 divided by 693.4. Now, the problem that a lot of students do, and I see this all the time, is you do 4,000 minus 3,152 divided by 693.4. And what happens? Oh, you get a drastically different number. Why is that? Because PEMDAS. This is going to read this as, please excuse my dear, division. So it's doing this division first and then subtracting that overall value from that 4,000. We want to only divide it by the quantity of the difference between these two values. That's just a little side note. I see it a lot. I just wanted to bring attention to it. So back where we were. So we got the z-score of the first birth weight one, the first data set. Now we need to get the z-score of body temperature. So same thing. I think that's a typo. Yeah, that's a typo. Let's see if I can actually edit that now. No, I can't. It's just a picture. All right, sorry about that. Just to give you a heads up, Pearson gives me PowerPoints to start with, and then I edit them as I see fit. Like I add my own slides, I take away slides I don't want. So sometimes I have control over things like this picture I do not, because it's a picture, it's not a text box. Just so you kind of know where your information is coming from. But ignore that 3. 99 minus 98.2 divided by 0.62 is 1.29. So we have a z-score of dataset 1 of 1.22. We have a z-score of 1.29 from dataset 2. So which one's the more extreme value? Well, clearly the 1.29 is more extreme. So we say that that is 1.29, or 99 degrees Fahrenheit is 1.29 standard deviations away from the mean of 98.2. Whereas 4,000 grams birth weight is 1.22 standard deviations away from the mean of 3,152. So since body temperature is further away from the mean, it is the more extreme value. Here's that visual again, or this is very similar to it. We say that 95% of all data values fall between -2 and +2. So then anything less than -2 or greater than +2, which falls in that green range, would be considered significant. Let's do another example. Is a platelet count of 75 significantly low? So the lowest platelet count in a data set is 75. Is that value significantly low? Okay, we need to know the mean and the standard deviation, and they give us that in the next slide, or the next sentence, I mean. So the mean is 290 or 239.4 and a standard deviation of 64.2. So we have our x value, our x bar, our mean, and our s, our standard deviation. Let's get a z-score. So we have 75 minus 239.4, and notice how since our value is less than the mean, we're going to get a negative z-score, and that's fine. So when we divide that by the standard deviation, we get a z-score of negative 2.56. So since that is more extreme than 2, it would be considered significantly low. Negative 2.56 would be somewhere over here, which is in the significantly low value region. The next topic is percentiles, and this is basically saying how far along are you of a data set? So say you have a data set of 100 data values, and they are in ascending order from least to greatest. So we are saying that the fifth value of that line constitutes the 5 percentile mark. The 50th would be the 50 percentile mark. P of 99 would be the 99%. And you often hear of these when maybe you're looking at how well you did on your SATs, and you say that, oh, I'm in the 66th percentile, or I'm in the 99th percentile, or if I'm smart, I'm in the low percentile, meaning that only this many kids are exceeding me with their SAT scores. So it's a measure of location, which divides a set of data into percentages along its line. So how do you find the percentile of a value? Well, it's just a simple little formula. You take the number of values less than x, and then divide by the total number of values. And that makes sense. If we had 50 total values, and then you look at the number exactly halfway, so 25. Well, 25 divided by 50 is 50%. So it'll be that formula right there. Let's go do an example. The airport Verizon cell phone data speeds listed below are arranged in increasing order. How nice of them. Find the percentile for this data speed of 11.8. Okay, so let's find 11.8, right over here. So when we have to figure out how many x values are lower than this value right here. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20. So we say that 20 data values are lower than 11.8. How many data values total are there? Well, 10, 20, 30, 40, 50. So it would be 20 divided by 50 times 100 gives me 40. So we are at the 40 percentile. So that means that 40% of the data values are lower than this, and 60 are going to be at or greater than this. So the P of 40 separates the lower 40% of values from the highest 60% of values. So just your notation, N is the total number of values in a data set. That's common. K is the percentile being used. So P of 25 right here is this 25 right here is the K value. L gives you the position of a value, and P of K percentile is just going to be the percentile of the given percentile being used. Okay, here's a little flow chart for you to use. So you start, you take the data, you sort it, you compute your L equals K over 100 times N, and then if is L, and this is where values can get different. Is L a whole number? If it's yes, take this step right here. If it's no, then just go over here. And that's just kind of showing if it's in between two values. So let's do another example, converting a percentile to a data value. So now I'm not giving you which number we are looking at and what percentile is. Now I'm telling you, I want to know the 40th percentile. Okay, so now we're working backwards, or the opposite direction from the previous example. So now we are proceeding with this. We have L equals K over 100 times N. So we have K equals 40 because we are attempting to find the value in the 40 percentile. So we put in 40 right here, divided by 100 times 50. We get L equals 20. Since L is a whole number, let's proceed to the box located to the right. So now we are looking at this scenario right here. The value of the kth percentile is midway between the Lth value and the next value in the sorted set of data. So we are going to say that it's midway between the Lth value and the next value. So that means that the 40 percentile is midway between the 20th value and the 21st value. Again, because L is a whole number, That means that we are looking at this case right here. We are saying that it is midway between this value and the next one. So we're looking at the 20th value and the 21st value. So we are looking midway between those two, 11.6 and 11.8. Midway between them would be 11.7. So slightly different values if you look at the data set and then tell you the 40th percentile versus if you're told to find the 40th percentile and then you have to find the corresponding data value. Okay. Now let's go on to something that I think is a little bit easier. Now we are looking at quartiles. Quartiles are measures of location, denoted by Q1, Q2, and Q3, which divide a set of data values into 4 groups with about 25% of the values in each group. A little wiggle room for rounding if the number of total data values isn't perfectly divisible by 4, but they should be no more than 1 data value more per quartile. So let's define each of these. Let's start with Q2 because it's something you already know about. So Q2 is the second quartile, and it is the same as P sub 50, and it's the same exact thing as the median. It's just the middle number. What does that middle number do? It separates the bottom 50% of sorted values from the top 50%. It's the halfway point. The first quartile is going to be denoted by P25. It separates the bottom 25 of the sorted data values from the top 75. And it is basically the median of the bottom half of the data values. It's the 25% point. It's a quarter of the way through. If you have 80 data values, P of 25 is going to be your 20th value. Third quartile, as you might be able to guess, it's P75, and it separates the bottom 75 of the data values sorted from the top 25. And it is basically the median of the top half. So let's look at an example. We have these data values right here, and I want to know Q1, Q2, and Q3. So sort the data from least to greatest, okay? Lowest to highest, okay. Next, find Q2, because that's an easy value to find. You know how to find the median. So Q2 is same as a median, so boom, 70 is Q2. Now I want to know Q1. So it's the same as the median of the bottom half. So we're looking at just the bottom half of data values, so the median of the bottom half is 68. Q3 is the median of the top half of the data values. So we're only looking at these data values right here. Q3 is 72. Okay, and another thing about Q is think of it as Q1 is going to be 25% of all the data values. Q1 to Q2 is another 25% of the data values. Q2 to Q3 is 25%, and Q3 to the maximum is another 25%. So here are some other values, and this their corresponding equations. Interquartile range, semi-quartile range, mid-quartile range, and then the 10 minus 90 quartile range. Okay, once we can get all those values, we are going to create a 5-number summary. So for a set of data values, the 5-number summary consists of these 5 values: Q1, Q2, and Q3, the minimum and the maximum. Nothing too crazy. And we are going to be working towards plotting these on a box plot, as you may remember from your algebra days. So use the Verizon Airport data speeds to find the 5-number summary. Okay, so they're already sorted, so that makes it easier. So we need to figure out these 5 values. Min and maximum are always the easiest. Minimum 0.8, maximum 77.8. Okay. Next, we have to find the quartiles. I usually do quartile 2 first since it's the easiest. So midway between all of them is going to be halfway between 13.7 and 14.1, which is going to be 13.9. Once I get that, we can find Q1, which is the median of the lower half of the data values, which is 7.9. and then the median of the upper half of the data values will be Q3, or 21.5. So now we have our minimum, our Q1, our Q2, our Q3, and our maximum. That is our 5-number summary. Now we are ready to plot that on a box plot, or a box and whisker plot. And a box and whisker plot looks like this. We say this is the box and these are the whiskers. Sure. So the way it's labeled is your minimum value, or your lower extreme, I like to call it minimum, is going to be this little end of the whisker right here. Then it's going to be a straight line over to Q1. Then it's going to be a box over to the median. And then the box continues up to Q3. And then you have a straight line from Q3 all the way up to the maximum. And what we are saying is this is 25% of the data values from the minimum to Q1. 25% of all the data values lie between Q1 and Q2. 25% fall between Q2 and Q3. And 25% fall between Q3 and the maximum. It's a way that we're showing spread. So now to construct a box plot, find the 5-number summary, construct a line segment extending from the minimum data value to the maximum, and then construct that box extending from Q1 to Q3, and then draw a line to measure Q2. So now let's construct a box plot of these values right here. Now we already know what we're looking at. So we're saying the minimum is 0.8, Q1 is 7.9, Q2 is 13.9, and Q3 is 21.5. So now we can look at this and we can say a few things about it. We can say that, well, these are all relatively even in length right here, but this is huge. So what does that mean for us? It just means that there's a very wide spread of the data values. Most of the data values fall in this region. So that would be skewed right. It would have a longer left tail, or right tail, I mean. Skewed right, longer right tail. Here's how you can construct it on your calculator. Just follow these steps, but typically you're not going to have to do that. Maybe for your project, but besides that, you're more analyzing a box plot than creating one. Okay. So then skewness. Now, if it was perfectly symmetrical, meaning that each of the quartiles have an equal length, then it would look like this, very symmetric. This length, same as this length, same as that length, same as that length, or relatively speaking. And that would be very symmetric. Negatively skewed would have a long tail over here. Positive skew would have a long tail over there. Okay, that was a longer section, guys, but I assure you it's a more important section than we've done thus far. So any questions, always email me.